Okay, in this lecture segment, we are going to introduce Green's theorem. But before I can do that, I'm going to define a few things that we're going to need to know. Okay, the first thing. Okay. A curve C in R2 is simple, okay, if it does not intersect itself. Except possibly at the endpoints. Okay, so let's draw a few pictures here. Okay, so this would be a simple curve. This would be a simple curve. Okay. This would not be a simple curve. And this would not be a simple curve. The equations for this, to represent this using equations, so let's say we have a parameterization for a curve that is R of t on the interval from A to B for t. Then we would say that simple means R of t1 does not equal R of t2 when t1 does not equal t2. Except possibly if T1 is A and T2 is B, or vice versa. So T1 is B and T2 is A. And so those would be the endpoints. Okay, one more term, a simple closed curve. We've talked about closed curves before, is one that is both simple and closed. So this would be simple closed. And this would be not simple closed. So what we're going to be looking at right now is simple closed curves. And I'm just going to state one more theorem, which is the Jordan curve theorem. And the Jordan curve theorem says a simple closed curve C in R2 is the boundary of a simply connected region D. Or put very simply, no pun intended, the simple closed curve has an inside and an outside. There are two regions, right? So maybe it's very obvious, like in a case like this, here's my curve C and here's my region D. Okay, so it's easy to see what is this bounded region, but sometimes maybe it's slightly less obvious. So maybe I have a curve that looks like this, right? Oh, how am I going to get back there? Can't cross over. Okay, and now when you look at this, well, this is definitely less obvious about where's region D, right? You'd have to be really careful to figure it out. I think we can sort of figure that region D is here. Let's see if I picked the right region. Okay, goes here. And, let's get this region. So you'd have to be really careful to say, okay, this point is in region D, this point is not in region D. And I think we've got it here. You can kind of tell now. All of this. Oh, this little bit here, this little bit here, and there we go, I've got it. So the region that I've colored red is obviously D, and then C is this curve here heading this way and around. Okay. All right. So the is that all I need to give you? One more definition before we go on to the theorem. Let C be a simple closed curve in R2. And let D be the simply connected region that it bounds. Okay, so when we talk about a curve's orientation is the choice of direction in which you choose to move along the curve. Okay, so let's say here's my curve C, and here is my bounded region D, right? Okay. I could move around this curve two different ways. So we define what's called positive orientation. C is positively oriented. Or has positive orientation if and this is just sort of a casual, easy way of explaining it, D is to your left as you walk along C. So imagine I'm standing on top of my paper here, and I want to be standing so that D is to my left. Which way am I walking? So here I am. I'm right here on this. I need to be walking this way, facing this way, standing upright on this curve in order for D to be on my left. So this would be the positive orientation or the direction to walk to say that C has a positive orientation. There is a notation for this. Okay, so the notation is, it's an integral with a little circle on it, like that. Okay, so we would say this is the line integral like written like this, but the circle gives you an extra piece of information where C is positively oriented. And this is, C is a simple closed curve, and P and Q are functions. I should say C is a positively oriented, simple closed curve. Okay, so now that we've got all of these preliminaries out of the way, we've defined simple, we've defined closed, we've talked about the inside and the outside of a bounded region, and we've talked about positive orientation. We are ready to state Green's theorem. Okay, Green's theorem. Okay, let C be a simple closed curve on R2, and let D be the simply connected region that it bounds. And let P and Q be differentiable functions on D. Then the line integral over C with positive orientation of P dx plus Q dy equals the double integral over the simply connected region D of partial Q partial x minus partial P partial y dA. Okay, that is Green's theorem. So what Green's theorem does is it takes, let's draw a picture here. C, D. Okay, it takes, Green's theorem relates a double integral over the entire region D of the difference between partial Q partial x and partial P partial y to a line integral over the boundary of the region with positive orientation of PDX plus QDY. All right, we'll talk more about what that means, and I'll do some examples and prove this theorem in the next 2 lectures.